hello Philippines, hello other parts of the world. Now we will be able to have a short vlogging or live stream short. Let's see it if this is gonna be a short live streaming. So this is gonna be designing a heat exchanger. Okay, so this is an example also of heat transfer. Okay, being one of the example of transport phenomena. Okay, let's go directly and illustrate this kind of problem. Though this is not a worded problem, but I just prepare some data out of it so that we can easily interpret it well. Okay, guys. So first thing to do is this: illustrate or further comprehension. Guys. So before going that, we need to enumerate the different types of heat exchangers. We have the finned heat exchanger. Okay, we have also the shell and tube heat exchanger, tube and tube exchanger, the spiral heat exchanger. Okay, the parallel flow heat exchanger. Okay, the double pipe, okay, counterflow heat exchanger. But my illustration this moment in time will be based on the double pipe heat exchanger counterflow because it depends on the type of heat exchanger. Okay, you will be able to solve because there's a somewhat difference in the formulas to be used, though it's not so many, okay, but a little bit similar of more of the formulas, but there's a little difference, okay, how to compute, like that, okay. So we need to illustrate first. How can we do this? Okay, so I have to draw here, right, so that we can you can see me while I am illustrating the diagram. The diagram or the sketch. Okay. So it's gonna be like this. Okay, guys. Oh my God. So this is gonna be our heat exchanger. Oh. Ah. Like this. Okay. And there's gonna be an opening here, somewhere here. Sorry, there's an opening, but it's closed. There's an opening on the two corners of the end. Okay, so let's assume that the steam and the water has been flowing inside this double pipe heat exchanger counterflow. Okay, so our temperatures, because again heat transfer, the driving force is the flow of the temperature from higher temperature to low temperature, or the temperature gradient. Okay, like that. So it's gonna be steam. So let's say steam, we denote steam as capital H. Okay, let's have declaration of the symbol or the nomenclature, and we have C as our water. Okay, C meaning water is naturally it is starting from cold, not really that cold, natural temperature. Okay, and then the steam starts naturally with hot, right? Okay, because it's already a steam. Okay, there's hotness in it as a substance. Okay, now we need to denote this as since steam, so the steam will go out, will go in here. So this is gonna be T capital H I. So this is THI, meaning the steam will go here. Okay, so steam, ganon, going downward. Okay, and then also, okay, and then go out, the steam here on the other. So it's gonna be THO, ganon. We designate temperatures because temperatures are our driving force in heat transfer. Okay, and this is gonna be heat transfer through convection, meaning to say this is a transfer of heat from a surface, could either be solid or a stationary fluid, to a moving fluid. Okay, meaning there's a movement of molecules in a fluid, could either be liquid, gas, or solvent, something like that. Okay, so there's no medium. Okay, like that. This is not solid. This is not conduction. Okay, okay. But the problem could tell us whether this is a conduction, convection, or radiation. Okay. But in here, this is just a sample problem that is not worded problem. Okay, like that. And then we have water coming here in this direction, like this. In this direction, the water, right? So it has a temperature of TCI, meaning inlet temperature of the water, because we designate water as C. And then we have also the outlet temperature of water, which is equal to TCO. This is still water that goes out, of course. If water comes in, then water also comes out. Okay. So this is TCO. Okay. Now, in our problem, let's say that the inlet of water that will go to the exchanger is, let's say, 25 degrees Celsius, right? So TCI will be equal to 25 degrees Celsius, like this. And we have also a THI equal to, let us say, 27 degrees Celsius, something like that. Okay, like that. Okay, so I elucidated, or I presented some data in order for us to solve what is being asked. Okay, then in here we need to find out what are the temperatures of the water that goes out, the TCO. This is question mark. Okay, this one, TCO. And then what is the temperature of the steam that goes out in here in the other corner? Okay, so this is gonna be the THO also. So two required, TCO and THO. So this is our required. Okay, like that. Okay, guys. So one TCO and two THO. Now we can solve this individually because the H represents steam and the C represents water. You cannot mix up the two. So individually you will solve this. Okay? So the main formula that we could be able to use here is the second law of thermodynamics, which is heat is equals to the mass, or the mass flow rate, times the specific heat capacity times the change in temperature. So it's gonna be QC of the water. QC is equals to MC. Just follow the code or the letter designated so that we can easily understand to distinguish it from the steam. So we have MC delta TC. Ganon. Look at it. Okay, you should be consistent in declaring your subscript in your variable. So in your THO also, we can get that one in the formula. QH is equal to MH times delta THO. Ganon. So let's say that you have a mass flow rate of, shall we say, 0.6 kilogram per second of water that flow in your double pipe heat exchanger. So it's gonna be MC here in the inlet. So MC is equals to 0.6 kilogram per second. Here it is in the inlet part, 0.6 kilogram per second. And then it's gonna be, let's assume also that it's gonna be a mass flow rate of the steam, okay, that also goes in the double pipe exchanger in here. So it's gonna be, let's say, 1.2 kilogram meter per second is gonna be your mH. Okay, so 1.2 kilogram per second. Guys, when you talk about heat energy, so aside from taking it down or remembering the concept that your driving force is the change in temperature, then you should also know that we need the specific heat capacity. Okay, so this is very important in the computation of heat energy. You get the point? The specific heat capacity is very important. Just like with convective heat transfer coefficient, okay, mass diffusivity, diffusion coefficient, thermal conductivity, thermal diffusivity, momentum diffusivity. Oh my gosh, my tongue was thrown. Something like that. Okay, so you have to take note the coefficient or the constant for that. And in here, our constant or coefficient is simply the specific heat capacity, or shall we say that simply heat capacity in other textbooks. It depends on the author of the book that they represented that it's gonna be specific heat only, and others saying specific heat capacity, and other book also saying specific heat capacity. But we are referring to the same terminology. Okay, that's the point. So let's just use the most precise and technical one or accurate one, which is specific heat capacity. So normally we will declare this as CP in most books, but in here let's just consider this as a C, and the subscript will matter only what is or what are the substances that will go in your heat exchangers. For example, you have the oil, it's gonna be CO. If you have the benzene, you're gonna be CB. If you have the chloroform, you're gonna be CH. Okay, if you have the alcohol, it's gonna be A. Here, since water, actually it's gonna be MH, but we declared water here as C, not to confuse with the H in the steam. Okay, because steam also is a water, but in a vapor form. You get the point, so double entry, so we could not represent the same subscript letter H for that. That's why we represent the subscript letter H for the specific heat capacity of the water that goes in your heat exchanger. Okay, so that we can eliminate duplication of entry, redundancies, and at the same time we will be not able to confuse our declaration of our variables and quantities somewhere in our computation. So that's only the main purpose, but it's if you understand really any variables, any letters you will put on the subscript, it doesn't matter. Okay, it's gonna be like that. So what is your specific heat of water or specific capacity of water? Okay, so I told you over and over again, I tell you to, or I told you to memorize the specific capacity of water, because water is the pure substance as very common all over the world in the planet Earth. Okay, so we need to memorize that. Okay, let's remember the physical properties of water. Okay, first, the density of water at 4 degrees Celsius is 1000 kilogram per cubic meter, 1 gram per ml. Okay, 1 gram per cc, or it's gonna be, you compute that 1 grams per ml is just cc, right? Okay, 1 ml is just equals to cc, something like that. That's what gram cubic centimeter. Okay, and I don't know what's the value of kilogram per liter, but we can convert that. Okay, I did not memorize, but having these 3 units alone we can convert that one. You get the point? So, and then pounds per cubic feet in English system, that is 62.43 pounds per cubic feet. And take note the temperature reference is not 25 degrees Celsius. Over and over again, I told you that it's 4 degrees Celsius. Okay, so that is the density of water. Okay, what else? The boiling point of water is 100 degrees Celsius. Okay, the freezing point of water is 0 degrees Celsius and 32.2 degrees Fahrenheit. So your freezing point, with the boiling point, okay, and then you have also the density, and here we have the specific heat capacity. The specific heat capacity of water is how much? So over and over again, I told you also that is 1 calorie per gram degree Celsius. This is equivalent to 4,186 joules per kilogram degree Celsius. Okay, And what is your latent heat of vaporization for water? Okay, your latent heat of vaporization for water is simply equal to 2,260 kilojoules per kilogram. Okay, and then in terms of calorie again, we have the 540 calorie per gram. Get a point? So anyway, when you can convert this one, this will yield the same as what I memorized now. Okay, as long as you remember one only value, then you can solve for the others. Okay, you get the point? And then we have also the latent heat of fusion. You know that one, the latent heat of fusion through melting of the water, something like that. Melting point. Okay, so from solid to liquid, right? The ice will melt from solid to liquid. So your latent heat of fusion is 79.7 calorie per gram, something like that. Okay? So your identification clause will be that the specific heat capacity is having the unit temperature at the denominator of your unit. Whereas this latent heat of vaporization, latent heat of fusion, latent heat of condensation, there will be no temperature unit in the denominator. You get the point? Something like that. Okay, it's only the energy. Okay, something like that. It's only the energy over the, something like that. You get the point? The energy over the mass. Okay? So, in those basic values and basic standards, we can easily plug in or substitute our basic formula in heat energy. So, in here, we will use the specific capacity of water in this kind of problem as 4,186, okay? 4,000, okay, 186 joules per kilogram. You get the point? Kilogram degree Celsius. Ganon. Okay? Okay, guys. So, muna siya atong kuan. Now, what is the steam? What is the specific heat of steam? Specific capacity of steam. So, this is the almost half of the value of the water. So, it's gonna be, as what I remembered, it's gonna be 2,100 plus 2,150 based on my memorization. Okay? 2,150 joules per kilogram degree Celsius. Now, what if we try to consider the three phases? Liquid water is 4,186 joules per kilogram degree Celsius. Look at it. And then we have also the steam for water in vapor state. We have 2,150. And then what is the specific capacity of water in solid phase? Meaning as ice. Right? Ice, steam, and water or liquid, three phases of water. So solid, what is the value of specific capacity as an ice? So nearly also equal to the steam, it is 2,050 joules per kilogram degree Celsius. I'm just only stating this to you in order we can have another knowledge, okay, for the ice. Okay, but we are not using that here because our substances that will flow here is only liquid water and the hot steam. It's no ice. Okay, I'm just introducing you a little bit of knowledge for the specific capacity of ice. Okay, because this is very common. We see this every day in our refrigerator, in our fridge. At least we know the specific capacity of ice, right? Okay, because we see this every day. Dili-dili ala tool. So at least we know as an engineer, as a scientist, or whatever, we will know the specific capacity of an ice. Okay, it is 2,050 joules per kilogram degree Celsius. Right? Ganon. Now guys, let's use this formula, this one. Okay, let's use this formula. But in here guys, QC equals to MC delta TC. So my brain cells work. Okay, so this is gonna be missing of specific capacity. Because I am listening what I am talking and I am seeing what is right, I am writing. For example, if you are in a certain speech in the public or you are an instructor, to your audience, if you are seeing what you write, and if you are hearing and listening what you uttered to them, then automatically, when you see it again, you will review it and you can correct it immediately. You get the point? But if you don't see it after your discussion, and it will take you 1 hour, 2 hours like that, and then the mistake is just very small. Okay, so it's just what we call as negligence or carelessness. Okay, like that. You got the point? So my brain cells work that this is MC plus CC times CC plus delta C. Okay, and in MH, CH, delta H, like that. Okay. Okay, guys. For example, if I will have a speech on the public and I will say 40 times 4, and that is very easy, right? Because it is elementary mathematics. After you say that one, because you hear it from your ears, you can correct that after 1 minute, after 2 minutes. And you will say 1,600. Okay, and that's too far, right? In mathematics, then you correct it, especially if you are an engineer or a professional, a lawyer, or a doctor, because it will speak for yourself of who really you are. If you will get mistake for a very, very, very simple math. Okay, just like this. Okay, the formula QC MC delta C, and I missed to put CC, the specific heat capacity. Okay, this is not a very basic math or a very simple math, but I still corrected it after how many minutes, right? You get the point? Just like that. Okay. Okay, because sometimes, what we uttered in public, what our contents in public will really speak of ourselves, of who really we are. Okay, the way we talk, the way we communicate, the way we give reasons, the way we post, like that. If we try to look at the content and the substance of what we talked, of what we write, so we can generally say that this guy is something like that, right? But then if you talk very superficial and then there's no substance like that, because you can distinguish what is a joke, what is a humor from fact or from serious statement. So you can say that hinay ka if you cannot, do that. You get the point? So just like this is a very basic example that I commit mistakes and I really corrected this after 2 minutes, 3 minutes, 4 minutes, like that. Okay? You get the point? So it's gonna be like that. And this is the procedure really. When you speak in front of the public, when you do your discussion in your classroom instruction, this is applicable to all. When you join competition, when you write an articles, you have to review, okay, so that it will be polished. After that, you can develop a very good article, and then so that it will be reliable into the public, that they really understand what you are talking about, and they really understand the content of your vlog, of your live stream, something like that. So it's very necessary to correct. That's why I'm always telling you guys, correct me if I'm wrong, something like that, because due to due to multiple learnings or knowledge that accumulated in my brain cells, it could not be denied. Sometimes I will forget. Okay, there's no perfect in this world, but it depends on the mistakes that you committed. Okay, but because it is very easy. For example, 8 plus 9 is equal 17, and your answer will be 18. It looks like funny. You get the point? And you are engineer, you are lawyer, you are a BS graduate or whatever, and you don't know how to add 8 plus 9. You get the point? And your answer is 18. So what can the people will say about that? So something like that, that's the logic point of view there, okay? So just like this, I got the mistake, and then I corrected that after a couple of minutes. Because I listen what I spoke to you guys, and I see what I wrote in the sheet of paper, like that. Okay? Then if not, due to, so many, knowledge in your brain cells, then you can correct me and object me also, I'm telling you every time. So they can issue an erratum in my job description, meaning an errors that's gonna be like that. Sorry guys, that I mixed up, I forget, or it's gonna be like that. Okay, so it will be declared in your job description after you upload your video in your YT channel. Okay, it's gonna be like that. Okay, so you have to correct. Okay, since I am only one here, nobody will correct me. I corrected myself. Okay, like that. So going back, and this is very easy formula really in chemical engineering. This is gas, and most commonly used formula, the QMCPDT and the PVNRT. If you don't know how to remember these formulas and you are not a chemical engineer, get the point? Because these are very, very, very basic. Kung sa singing contest pa, gas. You get the point? You always use that as your contest piece when you join amateur singing contests. You don't change your singing contest piece. It's just like that. These two formulas like heat and ideal gas equation are always used every time for chemical engineers, okay, and even also to other engineers, okay, something, and there's no reason you will forget this, okay. But if you are not really doing the review and you are no longer practicing to read, then you can sometimes forget. But what I mean, you can easily recall, okay. You got the point? Something like that. Okay. So, go back na talaga tayo. Okay. So, we have the specific capacity of the water and specific capacity of the steam. Okay. Time check tayo, guys, because I have another appointment. Oh my gosh. I budget my time because I have another appointment also after this. Okay. So, we're gonna be having the overall heat coefficient. Since this is only water, guys, so our overall heat coefficient for this one is the same. Because steam here and the water is just the same. Okay, one substance. Okay, we will be using only one. Okay, now, so what is our overall heat transfer for this? So, since there are a lot of temperatures and 25 degrees Celsius our basis, then we can get the overall heat coefficient. Assuming only that the overall heat, this is not a real value because I don't have to Google search. It will take me time also to Google search, right? So I have to say 70. That's what I remembered also. Okay, correct me if I'm wrong. It's gonna be 70. Okay, so 70, it's gonna be watts per meter squared Kelvin. Okay, so it's gonna be like that, the unit of convective heat transfer coefficient, something like that. Okay, because the thermal conductivity is watt per meter degree Celsius. It's gonna be squared meter at the denominator, huh? Okay, it's gonna be our U. This is designated as a capital U. So 70 watts per square meter, and this is gonna be Celsius. Or let's say Kelvin. Okay, this is hypothetical, meaning not really sure. I did not validate for the purpose only of discussion. And then if you are with me now, in front of me now listening, then you can also, refer to the Chemical Engineer's Handbook, the Purist Chemical Engineer's Handbook, the Chemistry Handbook, and the Physics Handbook, or any references you want in online data, research. Okay, because I am not really sure for the Kelvin degree Celsius for this, but since we know that Kelvin is usually the denominator of a standard unit, then I use Kelvin. Okay, like that. Okay, now you have the overall heat coefficient, this one U. Okay, and then you have the standard formula of convective heat transfer. What is that? In convective heat transfer, guys, you don't have to consider the length and thickness here. Okay, there's no denominator, it's only linear, meaning straightforward equation. There's no denominator. So our formula for heat, okay, this is gonna be, okay, the overall heat or the general heat for the two. Because this QC MC delta T, like that, this is the specific heat, okay, computed for each. But this is the general for the two, for the combined. So this is gonna be Q is equals to the overall heat transfer coefficient, like that. You get the point? Okay. And then times the area, okay, times delta T. So delta T here will be it's gonna be the delta TH of the hot environment minus the delta TH of the cold environment here. Look, Q is equals to UA delta T is equals to delta TH hot minus delta C cold. Okay, cold water, hot steam, something like that. Okay, now in here, we need to introduce another learning and knowledge, which is the number of units, number of heat transfer unit. We denote this as NTU. So number of transfer unit. Okay. What is the formula? Actually, this is number of heat transfer unit, but we eliminate the H or heat because we mean of transfer that is understood to be heat transfer in this context of the discussion. Okay, you got the point? It's gonna be like that. It's gonna be overall transfer coefficient UA over the C mean. Nakakaluka. C mean. What do you mean by C mean, Sir Sotero? So this is our equation number 3. So this is equation number 1, equation number 2, the individual heat energy, and equation number 3. So we have equation 1, equation 2, equation 3. Okay. Now, the U is again overall heat coefficient, convective heat transfer coefficient. The A is the area. Okay, and then the C mean, the specific heat capacity mean, how can we compute for this? So we have the C. C represents for the water. Okay, then we need to compute that through multiplying the mass flow rate by the specific heat capacity. That is the C mean. Okay, so let's try. C mean. Minimum, mean means minimum. Okay. Okay, C minimum. So, meaning to say, specific capacity at minimum. Okay, the C mean. Ganon. Okay. And that is referring to water because we designate water, liquid waters as C. Okay, so C mean. So C mean is equal to the mass of the water that flow inside the double particle exchanger is equal to equal to, I represent it as 0.6 kilogram per second. Okay, so it's in here. So C mean is equals to, or it depends on the situation. No, it is specifically you mean sorry, you mean M-A-N and M-I-N. Meaning mean, minimum. I see, C mean. So we have also to evaluate directly, which of the two is in minimum, right? Because we have to choose, because we have two substances here in phases. 2 phases and 1 substance, sorry. 2 phases and 1 substance. The vapor and the liquid. And it's all water. So what is your basis for this? For the C mean? We need to say, you have to compute individually. Okay, the C mean of the two. So let's go first with the water. But by looking only with the mass flow rate, we have an idea that water is flowing 0.6 kilogram per second. And I have also steam flows inside also 1.2. So you have an idea already, okay, that it's gonna be C mean, the bigger one will be your C mean. Or if you are confused, go directly with the formula and detect the proportionality. Okay, you get the point? So if you have the Q, because me, I could not go directly unless I don't have the few in it. So let's say Q is equals to mass specific heat capacity times delta T, and solve for the C equals to Q over, okay, Q over M delta T. So by algebra, You solve for the specific heat capacity because you are computing for the C min. And C min is the specific heat capacity. In order to determine the proportionality out of that and the relationship, you need to solve for the C in terms of the mass. And mass is the mass flow rate. So it's here. Q is equals to MC per dt, so C is equals to the Q heat over M delta T. So meaning, specific heat capacity is directly proportional to the heat energy, but inversely proportional to the mass. So meaning to say, the water will go in the double pipe exchanger is less than, or water is 0.6, and then the steam is 1.2. So meaning to say, C min of water is high compared to the C min of steam. So it's gonna be, we use the C min, the specific capacity of the steam to use in the C min. In order, we can compute the number of heat transfer unit, okay, which is very essential to compute for the overall efficiency of your heat rate of transfer in this particular type of your heat exchanger. So you will decide now, okay, just like designing. For example, I designed this kind of heat exchanger. So I will decide now that I will be able to use the steam heat specific heat capacity rather than the water because of the theory and the proportionality and relationship. That it's gonna be that I have a very high mass flow rate. Of course, my specific heat capacity of steam is less than to the water, because we are computing for the minimum specific heat capacity, which is necessary in the formula of the heat transfer, number of heat transfer unit, okay, by this expression. But if you are really in doubt, you have to compute individually so that you can determine which is higher, C min, and which is lesser, and go to the lesser to make it safe, right? Let's prove that our theory is correct, okay? Because I say we will use the steam, but let's prove. We will solve one by one, right? So C min of water. Okay, C min of water is equals to the mass flow rate, pila man siya, water, so 0.6 kilogram per second, okay, times the specific heat capacity of water, which is 4,186 joules per kilogram degree Celsius, pila man siya. Calculator, please. Okay. So let's prove it with specific capacity at minimum in order we can use that to compute for the number of heat transfer unit, which is very essential to compute for the overall efficiency of your double pipe heat exchanger counterflow. Ganon. Okay. Guys, are you still with me? Okay, so 0.6. Okay, guys, so it's gonna be like this. So 0.6 times 4,186 is gonna be 2511.6 for the water. 2,511.6 for the water. This is gonna be cancel. This is joules per second degree Celsius. This is our C min. Okay, now C min for water, how much? Oh, this is the water, right? For the steam, okay, so C min steam. So I have to put this C min C because this is for water. Let's be consistent. So C min H. C min H is equals to CH, or the specific capacity of steam, which is equal to 2,150 joules per kilogram degree Celsius times the mass flow rate of the steam, which is equal to 1.2 kilogram second. Cancel kilogram, so 1.2 multiplied by times 2,150. So it's equal to 2,580 is joules per second Celsius. Ganon. Okay. Okay, guys. So, nanatay ko So 1.2, so 2,580. Gukudra siya og C-mean. So, ang atong gamiton na C-mean ani ang kuan jud siya. So 2,000 ang gamay na value. Okay? So which is the C-mean C. If you're still confused, review. So 0.6 times 4186, okay, 2511.6, and then 2150 times 1.2 is equals to, okay, 2580. So our C-mean to be used is 2511.6 C-mean. Okay, because this is minimum compared to the other one for the edge. Now we use that here later, here to compute for the NTU. So NTU is equal to the overall heat transfer coefficient, which is 70 watts meter squared Kelvin times the area. Now, what is your area here, Sir Sotero? You did not even mention the length. You did not even mention the thickness of your opening. So what's going to be like that? In that case, class, if there's no given in area, we go back to the basic concept that we will assume an area of 1 square meter. Remember this is theory really. If we don't have a given of area, we have the basis of calculation of 1 square meter. Just like ideal gas, we need to consider 1 mole of an ideal gas. That is a gas for ideal gas, right? And then we have also to consider 100 gram of solution if that is for the problem regarding expression of concentration, right? Percentage by mass, like that. And percentage by volume, we will also take the basis of calculation of 100 ml of water. It's gonna be like that. If there's no specific given in your problem, you get the point? Do not be afraid. You can use basis of calculation for that. And I think this is also one of the factor that some will fail. Okay? Because we don't go back to the theory and we feel that there's no other data and then we cannot answer, we go to another question. But but in reality, we can use the basis of calculation normally at standard, okay, condition, operating condition, such like this. There's no area, but you need to use the basis calculation is usually 1 cubic, not cubic, 1 square meter as an area. Okay, we will multiply the 1 square meter. Again, this is only a basis of calculation because we don't have a specific area in the given, and the length of the pipe exchanger is not also mentioned, and even the diameter, the inside diameter and the thickness and outside diameter are not also emphasized. So we can have the basis of calculation. So wala na siya lagad sa ulo. You get the point? But you will start out with 1 in area, ha? It depends on the situation. But in the volume, you start with 100. And then in mass, you start also with 100 grams, 100 ml. Okay, like that, ha? You get the point? And in ideal gas also, we start with 1 mole. 1 mole of an ideal gas, like that. And then if it is an ideal solution with an activity coefficient equal to 1, then of an strong electrolyte, right? Strong electrolytes, just like a salt, a brine solution, okay, it has an activity coefficient of 1. Okay, so it has the ability to dissociate strongly in a solution. Okay, so grabe siya, electrolytic kayo siya nga substance, then ideal siya, ideal solution. Okay, so use also 1 mole of a strong electrolyte solution, meaning salt and water, not limited only to sodium chloride, but a lot. It could be sodium sulfate, sodium chloride, those are salts, right? Sulfates, a lot, phosphates, group, like that. Okay, so basis of calculation dito ha, why given. Get the point? So 1 square meter, okay, over C mean, which is equal to 2511.6. We carry over the units so that we can really distinguish what the units will be left behind after we solve. Something like that. So joules per, what's that? Joules second, oh my goodness, degrees Celsius. Oh my gosh! See, degrees Celsius. There's incompatibility, okay, with units. Okay, like that. So our numerator is watt per square meter Kelvin times 1 square meter. Is area cancel the meter squared. Okay, what will be left is WK. Okay, now in this situation, what you will be converting this, the 70, the coefficient, the overall transfer coefficient, or the specific capacity, which is easier to convert because the denominator is not agreeing. Okay, Kelvin and degree Celsius for ba siya? Okay, like that. So how can we do this? Okay, so either you convert the Celsius to Kelvin or either you convert the Kelvin to Celsius. So this is the rule. You get the point? So, unsa man ni mo ron? Now, kinama kay mga temperature. You get the point? Here, you have the temperature here. Right? So what is the temperature of water in going inside the, heat exchanger? Okay, so that is 25 degrees Celsius. Okay, so convert 25 degrees Celsius to Kelvin and then put that in your equation so that it will cancel to the denominator of K in your overall heat coefficient. Something like that. You get the point? Yes. So that you can cancel. Okay, you got the point? If you cancel that out, then there will be no unit. Because NTU, or number of heat transfer unit, is unitless or no unit. It will be cancelled also because watt, as I said over and over again, okay, this is equal to 1 joules per second in the formula of power is equal to work over time. So joules is the unit of work and seconds is the unit of time. That's why watt is the unit of power. That's why watt is equals to 1 watt is equals to 1 joules per second. If you substitute the joules per second instead of W, then the joules per second denominator of the specific capacity will also be cancelled. Okay, so let's cancel the break directly. So cancel joules per second. What will be left is nothing. Take a look. Okay, okay guys, so that we cannot multiply the 0.6 in the inlet, let's just assume that the overall heat coefficient for this, because this is only for the purpose of discussion, right? I'm not telling this that my data is perfect or my data are perfect. You get the point? So hypothetical meaning for the purpose of understanding, basic understanding, it's gonna be the way how it is being solved if you use double pipe heat exchanger, okay, and counterflow, okay. So we need to adjust this overall heat coefficient in degrees Celsius lang siya. To that, we can cancel directly to that specific capacity here in our problem. Okay, because it's 2 type 10 for me, I have another appointment. Okay, you got the point? So I will be late. Char. So I will cancel directly. I will change the unit of the denominator overall heat coefficient, overall heat transfer coefficient to 70 watts per square meter Celsius, so that I can cancel immediately with a specific capacity. Anyway, this is only, for the purpose of discussion, okay? It will take time for me to add to 73 like that. Anyway, it's very easy to multiply with or to add, but let's just direct, as long as we understand, right? Okay, cancel. So let's do this multiplication. So 70 divided by 70 times 1, which is the area, divided by 2511.6. Okay, 70 divided by 255. 70 divided by 2,570. Sorry, divided by 2511.6 is equals to 0.028, our number of heat transfer units. So NTU is equal to 0.0278. NTU is equals to 0.0278 or 9. Ano na siya kung NTU? Okay? You got the point? Charot. Okay. Now, what is our formula for the overall coefficient. Why we go to this? Because we cannot obtain the TCO and THO without having these quantities, overall efficiency and TU, like that. You get the point? Okay. So we have the formula of overall efficiency is equals to the heat, the actual heat being transferred overall between the two over the maximum heat. Okay, like that. This one. This is equation number 4. Our equation number 4 will be equal to the overall efficiency of your heat transfer, overall efficiency of your heat transfer is equals to the heat energy of the actual between these two, water and the steam, over the maximum of heat between this combined, maximum siya, like that. So our heat will be Q is equals to overall efficiency over times Q max. So this is coming from our equation number 4. Q is equals to efficiency times Q max. From algebra, we cross multiply to obtain this formula, right? Now, we can solve for the Q max, but we cannot solve for the efficiency because we don't have the values. So how can we do this? We have another also formula for the efficiency. Efficiency is equal to equation number 5. Wow, there's a lot of equations and only one type of, heat exchanger. So question number 5, formula number 5 class. How can we do this? Oh my gosh. So our equation number 5 will be will be efficiency is equal to 1 minus, this is quite difficult. When you derive this, you can derive this formula, but me, I just memorize because, I already know a little bit for the concept. If you want to derive, then you will derive this formula. You can make it by correlating some formulas, right? But it will take time for me also to do this. That's why we go directly to the overall efficiency formula that involves exponential. So overall rate of heat transfer is equal to 1 minus the exponential of the number of heat transfer unit, negative, times, 1 minus the NTCR. Natay ba kung i-introduce guys? CR. What is CR, Sir Sotero? CR is the ratio of the C mean to C max. Diba? We have the C mean, the specific capacity of this water here, 251.6, and we need also the C max. Good the point. Ang C max, katong dako siya, nakuha nimo, in which that is 2580. So it's gonna be 2511.6 over 2580 here, which is lesser the C min, which is the higher the C max. So C min over C max is equal to CR. It is not comfort room. It is specific heat capacity ratio. That's why CR. Because the C is specific heat capacity and that is ratio R. That is CR. It's not comfort room. You got the point? So CR is equal to C mean over C max. Mean means minimum, max means maximum. So the ratio of it is our CR because it's in here in the formula of the computation of overall of the rate of heat transfer. Ganon. So over 1 minus CR times the exponential of the number of transfer unit, heat transfer unit, again, 1 minus CR. Ganon. So this is gonna be our formula. Take note guys You memorize this very easy because, it involves an exponent. And then there's 1. And then 1 minus something, blah, 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 chu, blah, chu, chu. And then the exponential will be raised to a certain thing. And there are only 2 quantities in the exponential form. And it is the same from the top and the bottom. And then this only be multiplied by so it's gonna be the mode of your memorization. Okay, so that you can easily memorize. You will understand the orientation, how many quantities, and the first, the first quantity, so that it's very easy, or what is being repeated. Okay, just such like the overefficiency, 1 minus exponential, plus upper parenthesis, negative NTU siya, negative yun siya, and then times 1 minus CR. But nasa siya sa ubos. Okay, 1 minus exponential, close upper parenthesis, negative NTU, 1 minus CR. Yung taparan ninyo og CR. Umura na yung diferensya. So that you can easily memorize. You will detect the difference. Okay? Or how it is being possession, how it is being oriented, and what is really the first, letter for that particular code or subscript or nomenclature or symbol, so that you can stack that in your brain cells. You get the point? Okay, just like it's very easy to memorize, right? At first you will say, it's very difficult because it's an exponential. But take note, if it is done repetitively, something like that, in always the same, it's easy to memorize, really. Okay? So E will be, now we have the value of NTU, now we will compute for the CR. Meaning the ratio of the specific capacities of water and steam. Okay, CR, C mean is here, 2511.6. Okay, 2511.6 over C max is here. Okay, your C max, the specific capacity at maximum value, is 2580. Okay. And then class, we don't have to put unit because it's understood that these are all specific capacities, and then their units will be automatically cancelled because CR also is unitless, the same as C minimum and C maximum. Okay? It's gonna be like that. So your CR will be how much? So calculator please. 2511.6 divided by 2580 is equal to 0.9734. This will be your CR, 0.9734. So if you have now your CR, then you can substitute this in your equation of your overall efficiency of rate of heat transfer. Substitute one by one. Since we have the same quantity, then solve that quantity and then substitute later, because it involves exponential. It's very difficult to do it. Okay, so let's say exponential of NTU. NTU is our value here is somewhere like this. Okay, so we compute the value as, okay, where's our value? And you did not compute first. We compute first because we have already the values plugged in. So 70 times 1 is equals to, divided by 2511.6 is equal to 0.28, right? It's here. 0.0279, round off. This is our NTU. So, okay. So, negative 0.0279 minus 1 minus CR. CR is here, 0.9734. Okay, guys. This is only directly substitution now. If you have the given, then you can easily substitute for the given formula. So, in here, our answer will be, okay, exponential. We cannot do this by by brain cells, because it is exponential to negative something, ganun. Okay, 1 minus 0.9734 is equal to 0.0266, okay, times 0.0279 negative is equal to, so 7.42, charot. 7.42 times 10 to the negative 4 exponent. Okay, and this is negative because our NTU here is negative in the formula. See? Okay, now exponential of this quantity. Okay, so shift exponential, scientific calculator. Okay, 7.42 exponent to the negative 4 is equal to 1.00007. Oh my gosh. So this is 1.00007. So 1.0007. So this is our, this one. our exponential. Then substitute in the efficiency formula, then we're gonna say that E is equals to 1 minus 1.0007 over 1 minus 1.0007, okay, like that, times your CR 0.9734, and your efficiency will be chuba chuchu, okay, kaloka. So 1.0007 times 0.9734 is gonna be 0.27 minus 1 is equals to like this, 0.026, okay, 0.026, 1 minus 0.0000, charot, 1 minus 1.0007 is equals to 7 times 10 to the negative 4. Get the point? 7 times 10 to the negative 4 divided by 0.026 is equals to 0.027. Okay, this is your efficiency. 0.27, your efficiency. And now you have the efficiency already, 0.027. Okay. And then you have the formula, which is Q is equals to Q max. Substitute that here in your E. Okay, like that. You get the point? Substitute that here. And how can you solve for the Q max? Q max is just very, very easy. You can compute that through, okay, Q max, QMCP delta P. You get the point? And then you go to the higher value, which is in here. The higher value will be your water here. Okay? Well, it depends when you solve it one by one, which is the having the higher heat energy. Then you will substitute that here, the Q max. This is not adding Q of the water and the Q of the steam. It's not like that. You will just choose among the two which have a higher heat energy, and you can substitute the Q max because they are just combining into one in entering the double pipe heat exchanger. So that will be your Q max. You got the point? Now this is not yet our answer because we need to compute for the THO and the TCO. Now by going back to the problem, guys, okay, how can you interpret the TCO and THO? Okay, so go first with water. See the drawing. Okay, like that. See the drawing. So the TCI will go there, right? Will go there in the right. Okay, and then the TCI will go also in the right. But in heat transfer theory, it should be from high temperature to lower temperature. Normally, it's gonna be TCO has the higher temperature. It will deviate, guys, to a little bit with the theory because we have steam coming in the bottom corner. You get the point? When the steam going to the bottom corner, it will receive the heat of the water. You get the point? Because this is open. When this water receive the heat of the water that flow out, so your TCO of the water will become higher to the TCI. You get the point? Because the TCI at first is not hot. So it's gonna be TCO minus TCI. Okay? Because it's gonna be high temperature minus lower temperature. Okay, moment na siya ang flow of the heat transfer, right? Higher temperature minus lower temperature. Okay? But in here, TCO minus TCI siya. Okay? So, delta TC, ganon. Kaloka. Delta TC, meaning water. Change of the temperature in the water. Okay, of the water that goes in the double pipe exchanger is equal to TCO minus TCI. I show you the drawing, right? TCO minus TCI. So, my gosh. TCO, TCI. Ano ka? Wait ha. with mga friends. Okay, TCO, TCI. In here, in the illustration again, the TC is equal to TCO minus TCI. You get the point? Okay. So, delta TC is equal to TCO minus TCI. This is equation number, kapila naman yung equation? Gosh. Equation something, equation number 6. Equation number 6. Muna siya. Delta T is equal to TCO minus TCI. Okay, now the problem says what is the TCO, the outlet temperature. So you will solve for TCO by algebra. Transpose. This linear equation only is very easy. How can you transpose that? So TCO is equal to delta C plus TC1. Okay, so TCO is equals to, wait, okay, delta TC, okay, delta TC plus TC1. This one. And now you will say to yourself, so Sotero, what is the value of delta TC? So this delta TC, you can obtain that in your MCP delta TC. Okay, this delta TC. Delta TC, you can obtain that in your MCP delta TC. And in that, solve the value of delta TC. So delta TC from your equation MQC, MCC delta TC is equal to, I don't have to show because it's very elementary. So delta TC is equals to QC, MCC, CC. So I told you, develop really algebra. Okay, so TCO is equals to, solving for delta TC, so it's gonna be QC. QC is not quality control. This is cool water, huh? We represent C. Okay, so QC is equals to MC. Okay, guys. Okay, gonna be QC, MC times CC. Okay, muna na siya. Plus TC1. This is equation number 7. In your equation number 7, bingo, you can solve the value of your TCO. Why? Because you have the QC. Okay, the QC for the water in here. You can solve. See? MC, mass flow rate, specific heat capacity times delta TC. Okay, so what is delta TC? Meaning, okay, meaning the muna siya ang natabo. So, outlet minus inlet. You got the point? So, delta TC naman ito sa water. Naman siya diri, oh. Okay. And then the other one also, guys, sa water and then sa THO. Okay, THO. How can we solve this? So, delta TH. Take note the direction, ha? This is very important, the direction. The direction of the flow, this is counterflow. Going here inside the corner of the exchanger. So this is THO. Okay? And then we have also THI going the same direction. Downward. So it's gonna be negative THI minus THO. This is equation number 8. Then solve for the value of THO. Okay, because downward is always negative by signs. Okay, so you're gonna do this or reverse that one. We're working now for algebra. Okay, transpose like that. Okay, delta TH is equals to, let me show you after I analyze. So delta THO. Okay, delta TH. Okay, then plus TH1, and then, okay, ganun siya, chuba-chuchu, okay, ganun. So, both divide by negative 1, so THO is equals to, wait, ha, so, it's gonna be delta TH, okay, minus delta TH1, negative delta TH, and negative THI. Okay, like that. Okay, got the point? So again, review. Negative delta HI minus THO is equal to delta TH. Solve for the value of negative THO. So negative THO is equal to delta TH plus THI. And you don't want a negative THO, so simply THO divided by positive, then negative delta TH, and then minus THI. So this is going to be equation number 9. Okay? This one. Okay, guys? Okay, puro man siya negative. So, THO negative, THO positive is equals to delta TH man siya. Okay? You got the point? Okay? And then, if there is a higher value, it will become positive. Okay? So, this is your equation 9, equation 8, equation 7. Okay? Now, you can solve for delta THO again by using specific heat capacity in your Q. So, your QH will, your delta TH is equal to QH MH CH minus TH1. And bingo, you can solve for your value of THO. So how can you solve for your QH? Oh no, QC first. QC is equal to MC CC ganon delta TC. Okay, ganon siya. So ano yung Q? So it's gonna be MC, pilatong MC. So this is gonna be, calculator please, charot. 4186 times specific heat capacity 4186 equals to, okay, 4186 times CC is equal to 0.6, right? Okay, water na siya. Okay, so 2511.6 delta TC. Okay, guys? Delta TC. Okay? This is equation number 11. And then your QH, okay, your QH will be, okay, QH is equals to MH, which is 1.2, times CH, which is equal to 2150. Then there will be, this is delta TH, right? So, QMC delta TH, ganun siya. Okay, so muna yung heat, right? So, yung makita mong kag-heat, so delta TH. Okay, so 1.2 times 2150 is equals to, so 2580 delta TH. Okay, ganon. So, we have delta Q. Okay, and you can substitute na talaga siya by having this equation. Ayaw yung kadlok guys, nga napa siya subscript, napa siya, kuan ba, i-substitute na nimo diri siya nga equation sa 9 and 10, sa, okay, sa 7 and 10. Okay, sa 7 and 10 here. Okay, sa 7 and 10 class. Okay, so 7 and 10, you will substitute this equation number 11 and equation number 12. Take note, there's delta TC and delta H. And then this subscript, if you substitute that in here, you do the math, okay, and substitute values, somewhere will cancel all throughout. I don't have the time anymore because I have an appointment. Okay, then you can solve for the value of the THO. You get the point? Because we have THI. You get the point? And your QH is delta H. And now, so that you will never be confused, there is a direct way of analyzing this. Okay, like that. Since you know already your Q here in your efficiency, right? Here. Individually. So just use the mass individually. Just use a specific capacity individually. And the heat energy individually. Now for the QH, use the formula individually. This one here. Okay? QC, MCC, CC like that. And use the inlet for C, and use the inlet also for H. So that will be your QH for steam. Kailangan tayo inlet temperature sa steam. Okay? So more, okay, you got the point, inlet temperature sa steam. Yan, nasa ka inlet temperature siya, you have also the inlet temperature of your water. So you use that H individually to substitute in this equation, 7 and 10. Okay? Here. 11 and 12. Here. You get the point? After that, substitute it to 7 and 10 equation, then you can solve for the value because the Q is already there. See? THO is equals to QH, and we have all the heat of QH, right? MC, mass, given tanan, specific heat mass, inlet temperature, given tanan. O, di ba? So, makuha na nimo. So, muna yung answer diara. So, minus nimo ang TH1. Ang sa kay TH nga 25. So, na kay TH, you have THO. Okay, number equation 7. Okay, ako siya. Na kay QC, individual heat energy sa water. O, MC, specific capacity, times mass flow rate, times, the delta T, the Nnet, we will use the Nnet, okay? And then plus TCI. Ganun siya. Makuha din mo siya ang value. May buong ka nung you don't consider the outlet. Because in this equation, it involves the outlet already in this equation here, in 7 and 10. Kasi 7 and 10. Di ba in our derivation, inunta, di ba? Delta TC is equal to TCO minus TC1. TCO is the outlet temperature already. That's why when you compute here, with the heat here, no need to carry over the outlet temperature in this first quantity. Kay duplication of entry naman siya, or redundancies. So that's why, ang inlet lang siya ng temperature. Kaya nag-add na ba yung katriotis, okay, TCO minus TC1, gano'n nun. Okay, so mag-double makasa yung temperature. So muna, ang imong QH sa steam ni mo, inlet ra temperature sa steam nga mo ni siya 27 degrees Celsius. Okay? Nakakuha muna siya. And then sa water also, ang inlet temperature nga 25 degrees Celsius plus 273 siya. Okay, kay Kelvin man siya. Ganda nun siya. Okay, any questions so far? Okay, wala na good time. Sorry for that. Charot. Any questions so far? And then if you have also an equation like this, guys, don't be afraid also, guys, ha? Na yung mga subscript, na yung mga coefficient na wala pa'y value, because if you try to substitute it to another equation, let's say equation 8, equation 7, it will just also be cancelled somewhere along the way. And then plus the units, then it will be simplified later on. Okay? That's why I told you there are two methods for this, but the safe method is the other one, using there is already value of the heat. Okay? Ganon siya. You get the point? You get the point? This one, overall efficiency, makuha din mo ang Q pod ani niya. Okay? You get the point? Kay makuha naman nimo ang delta THO and delta THO, TCO. Okay? So water ang ano siya, values. You get the point? This is very clear, right? Any questions so far? Okay. Any questions so far? Okay. So, ang imong Qmax ani niya, guys, ha? Imong yung timanan ang asay maximum ani niya. So, para makakuha na kag Q. Okay? But then, guys, there's three options right ang possible ani niya. The first option is individual heat, and the second option will be the true kanisha na pay subscript. And the third option will be using the common Q for the 2. This one. And then using the maximum C min. Okay, so kung using the Q maximum C min, that would mean that that is the heat for the 2, which is Q. And then you substitute that here, meaning to say the QH also will be your Q for steam, and your QC also will be your Q also for the water, because they are in equilibrium with each other. This is also another theory for that. I cannot prove because I don't have time anymore. You get the point? Actually, in the discussion, in the reference, there's no such like that an explanation. I draw my own, options how to solve this. You get the point? Because it's very direct in the reference, and it leads me to think a lot before I discuss this. Okay? Okay, it's very clear right now. Okay, first option, class, is to use the individual heat of the water and the steam. The second option will be using the Q in this, having the efficiency formula, then letting this Q as the Q of the two because they are in equilibrium with each other, in using the 7 and 10 so that we can get the THO and the TCO. And the third option, this one, using algebraic expression by having the variable and substitute this quantity to the 7 and 11 equations, then you can simplify further and you can get also the heat there and compare your answers. If it is the same, then bingo, that is the best, that is correct. Something like that. And then you can go back to your reference if you are getting the same answer. Okay? Because in here, guys, honestly, I made my own data. Okay? So I don't depend in the sample problem. I made my own data. For example, if the overall heat transfer coefficient is like this, and then since I told you a while ago, it's hypothetical, I don't copy. I just have my own here. So that it will, you know, it will help. It will push me to think and understand well if I have another given. Okay, like that. You get the point? In here. This one. Okay, so it's gonna be like that. Any questions so far? Okay, if you don't have question anymore, then you can comment down below in the comment section. You can subscribe to my YT channel if you are not subscribing yet to my YT channel. Thank you so much. Bye-bye. God bless everybody. See you later. My gosh. Hello, ka?